All right, and the last part of this lesson is dealing with exponents. So that's what we're going to be looking at here. We're going to start with basic integer exponents, what an exponent represents, then get into some of the complicated, or not more complicated, but not super complicated properties dealing with what happens when you multiply and divide with a common base, and then we'll get into some scientific notation. So here we go. Integer exponents. Exponential notation is used to shorten products of factors that repeat. For example, if I had the number -3 times itself 4 times, I can rewrite that as -3 raised to the 4th power. Same thing with the 2x plus 1. If I had 2x plus 1 times 2x plus 1, I could rewrite that as the quantity 2x plus 1 squared. So in general exponential notation, it says let a be a real number, variable, or algebraic expression, and n be a positive integer, where n is the exponent, a is the base, and a to the n is the nth power of a, read as a to the nth power, or the nth power of a. A key to making sense of exponential expressions is identifying the base. The base is a repeated factor when we compute the value of the expression. So we have to be careful with exponents. Sometimes people, if you're not careful, the order of operations will get you. I'll do a couple here with you, and then you're going to try a couple on your own. What I mean by that is if I have -3 raised to the 4th power, that really means -3 times -3 times -3 times -3. And if I wasn't careful with this, it'd be really easy for me to make a mistake with the signs. But if I think about this, a negative times a negative is a positive, times a negative is a negative, times a negative is a positive, I know my answer is going to be coming out as a positive. 3 times 3 is 9, times 3 is 27, times 3 is 81. So I know this is actually, when I simplify this, positive 81. And to illuminate how we could have easily made a mistake, there is a difference between the number -3 raised to the 4th power and negative of 3 raised to the 4th power. This negative of 3 to the 4th really means -1 times 3 times 3 times 3 times 3. In this case, my base is 3, not -3. So I have to be really, really careful with that. I can see my base here. And if I don't have the right base, things are going to get messed up. Well, now I am going to have a negative number coming out because I just have a negative times a bunch of positives. And 3 times 3 times 3 times 3 was 81. So this is really just -1 times 81, which is the same thing as -81. So if I'm not paying attention with the bases, I could make a mistake. What I'm going to ask you guys to do right now is take a quick pause and try these other two. I'm going to ask you to expand these exponential expressions. All right, here we go. The base of this next one is 2. 2 times 2 times 2 times 2 times 2 is 32. The next one, the base is -1, so I can just see how I'm going back and forth between a positive and negative number. -1 times -1 times -1 times -1 times -1 is going to be -1. All right, from there we need to look at some of the other exponential properties we have. First one we have is when I'm multiplying with a common base, I'm adding my exponents. The next one we have is that when I'm dividing with a common base, I'm subtracting my exponents. Next one we have is that if I have any base raised to the 0 power, that's just a fancy way of saying 1. Next one, we are seeing that if I have a negative exponent, I have to make that number, that exponent positive, but it gets reciprocated. Next one is I have an exponent on a grouping. I really take this exponent and I distribute it to each number in that grouping. Next one, if I have an exponent raised to an exponent, I'm just multiplying my exponents. And last but not least, basically the same thing that we had when we had the exponent on top of a product. If I have an exponent on top of a quotient, it's the same thing. This exponent gets distributed to each one of those parts of that division, the quotient and the dividend. Okay. When asked to simplify an expression involving powers, rewrite it so that each factor appears only once. All exponents are positive, and exponents and constants are combined as much as possible, as shown in example 7, which we'll do here in a second. I do really, really need to emphasize this to you, that because multiplication is commutative, and we're looking at simplifying complicated expressions that have exponents, and exponents just mean multiplying a bunch of times, there are so many logical ways to attack these because multiplication is commutative. So the way I think through these problems may or may not be the same way you would think through the problems. There's nothing wrong with that. What I'm going to do is I'm going to model my way through these first 3, and then I'm going to ask you guys to do 2 on your own. So the first one, it says simplify the expression, and I'm going to go ahead and take care of the coefficients first. So I'm thinking about the 2 times the 5. I know that 2 times 5 is 10. I am then going to take my a times a squared. If I'm multiplying with a common base, I'm adding my exponents. 1 plus 2 is 3. And I'm going to do the same thing with my b's. I have b cubed and b to the 5th. I'm multiplying with a common base. 3 plus 5 is 8. Okay. Next one, again, there's a lot of different ways you could approach this. What I am going to do, oh man, there's so many ways I could attack this. What I'm going to do is I'm going to I'll just do it all in one step. I'm seeing the same base in the top and the bottom. I know that when I'm dividing with a common base, I subtract my exponents. So in this case, I see u squared divided by u to the negative 1. When I'm dividing with a common base, I'm subtracting my exponents. So I'm thinking in my head 2 minus negative 1. 2 minus negative 1 is 3. I'm going to do the same thing with my v's here. V to the negative 2 divided by V to the 3rd. When I'm dividing with a common base, I'm subtracting my exponents. Negative 2 minus 3 is negative 5, so I have V to the negative 5. Now I cannot leave my answer written like this because I do not like this negative exponent. This negative exponent has to become positive, but the whole thing has to get reciprocated, which means I'm going to rewrite this as U to the 3rd over V to the positive 5. Next one, again, there's so many ways you can approach this. I'm going to handle that negative sign right away. If I have a negative exponent, I have to reciprocate the whole thing, so I'm going to rewrite this as 2 over x squared to the positive 3. And then once I have that negative taken care of, I'm going to take and I'm going to distribute this exponent of 3 on top of each of those. I have 2 to the 3rd, and I have x squared to the 3rd. 2 to the 3rd is just 8. 2 times 2 is 4, times 2 is 8. X squared to the 3rd, well, if I have an exponent raised to an exponent, I'm just multiplying, that is x to the 6th. What I'm going to ask you guys to do right now is pause and try this on your own. We have a couple down here. I'm going to ask you to simplify to the best of your ability. All right, and here's what I ended up getting. The first one, I ended up distributing that 2, simplifying that first little grouping, and then taking care of the 9 over 3 and the y to the 4th over y squared. I end up getting 3x to the 4th y squared. Second one, I end up taking the negative, getting rid of that right away by reciprocating, and then distributing 3 to everything. I end up getting x to the 3rd, y to the 3rd over 8. All right. And then sometimes what we'll do is we'll use those ideas of exponents to help us communicate really, really, really big and really, really, really small numbers. Specifically, one of those tools is called scientific notation. Used this a lot in science class in the past. You probably used this in math class in the past. We're just going to revisit it. Any positive number can be written in scientific notation. C times 10 to the m, where 1 is less than or equal to c, which is less than 10, and m is an integer. That just means when I'm writing this thing in scientific notation, my first number needs to be between 1 and 10, and I'm going to be just changing that into being multiplied by 10 to some power. This notation provides a way to represent very large and very small numbers. For example, the distance between the Earth and the Sun is about 93 million miles. In scientific notation, I could write that as 9.3 times 10 to the 7th mile. It's just a little bit more efficient at communicating those really big numbers. The positive exponent of 7 indicates that moving the decimal place in 9.3 to the right 7 places produces the decimal form of the number. The mass of an oxygen molecule is about 0.000000000000000000000000000000054 grams. In scientific notation, instead of writing all those zeros, we could write that as 5.4 times 10 to the negative 23. The exponent of negative 23 indicates that we would have to move the decimal point in 5.4 to the left 23 places to get this thing in decimal form. So, first thing we're going to do is we're just going to convert back and forth between scientific and decimal form. So the very first one, we have 2.375 times 10 to the 8th. All we're going to do is we're going to take the thing and rewrite that in decimal form. Easiest way of doing this is 2.375. Taking that decimal, I'm multiplying by 10 to the 8th, which means I need to move my decimal place 8 places. 1, 2, 3, 4, 5, 6, 7, 8. Which means my decimal place would now be all the way over there. So if I wanted to write this thing as a decimal, it would be right here, 250 232,500,000. There we go. Next one, same exact idea, but this time we're going from the decimal version to the scientific notation. I need to count how many times I move the decimal place. In this case, 1, 2, 3, 4, 5, 6, 7 to get to 3.49. So I have 3.49, not just 3. 3.49 times 10, and we moved it 7 places, and we moved it because it's a really small number. We have a negative exponent. So 3.49 times 10 to the negative 7. And what we can do is we can combine the skill of changing back and forth between big scientific numbers, scientific notation numbers in decimal form and scientific notation, and with some basic arithmetic. So that's what we're going to do here. So we're going to kind of show how we can handle these really big, scary numbers without using a calculator and just using scientific notation to help us communicate and do this stuff efficiently. So it says simplify 360,000 times 4,500,000,000, all divided by 18,000. Again, there's a lot going on there, but if I were to convert all these from decimal to scientific notation, I'm going to see just a bunch of really manageable numbers. I see 3.6 times 10 to the 5th, because I had to move my decimal place 5 times. I see 4.5 times 10 to the 9th, because I had to move my decimal place 9 times. And in the denominator, I have 1.8 times 10 to the 4th, because I had to move my decimal place 4 times. Now, the reason why I'm doing this is because multiplication is commutative. I can handle those kind of not perfect numbers in the front, and then the 10 to the 5th, 10 to the 9th, and the 10 to the 4th, I can just use basic exponent properties. So what I'm thinking in my head here is 3.6 divided by 1.8 is 2. 2 times 4.5 is 9. So my answer is going to be 9 times 10 to some power. And then I just need to think about, how do I get the exponent? Well, when I'm multiplying with the common base, I add my exponents, so 5 plus 9 is 14. And then when I divide with my common base, I subtract my exponents. 14 minus 4 is 10. So I can write this answer in scientific notation as 9 times 10 to the 10th. If I want to write that in decimal form, I can just take that and I can move my decimal place 10 times. So it'd be 9 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros at the end, aka 90 billion. Your turn. Here's a question. You can do very similar things to it. You don't even have to convert it into scientific notation. But I'm going to ask you to take these scientific notation expressions and simplify this thing. Here we go. Again, I handled just the numbers in front. 5.2 divided by 2.6, I lucked out as 2. 2 times 1.3 is 2.6. That's something you can do in your head. When I'm handling my exponents, 10 to the 3rd times 10 to the 5th is 10 to the 8th. 10 to the 8th divided by 10 to the negative 2. When I'm dividing with the common base, I'm subtracting. 8 minus negative 2 is 10. So I can write my answer as 2.6 times 10 to the 10th. Or if I wanted to, I could change it to decimal form. If I change it to decimal form, I can write it with all those zeros afterwards, aka 26 billion. There is your first prerequisite lesson. Again, more than likely you won't need to ever watch this video, but if it's here, if you do need a little bit of support, we looked at interval notation, inequalities, basic algebraic properties, and then basic exponent properties.